first of all, this time we want to move away from the most common situation where directional information, like vector field information, is summed up along a path. So this is what we're doing here. It's also sometimes called a path integral of type 1. So it's in a certain sense, it's simpler than integrating a vector field along a path. But also, on the other hand, it has to be interpreted, or it should be interpreted in a meaningful way. And this is what I've tried to achieve when setting up this exercise. Well, just follow me in my thoughts. What do we have? We are in a situation, or we assume a situation, where there is a certain electric charge distribution in space. And this is described by a so-called volume electric charge density, which you all know. It's first of all, it's a non-directional information given here. And this information is explicitly described by a scalar field, you could say. We can say scalar field every time we have a function in space using two or more, in this case, of course, 3 independent variables, x, y, z, Cartesian coordinates. And this is physically given to be, this is the standard symbol, you know, it's the minuscule Greek letter rho. This is just the standard symbol for densities in physics, and the unit will be electrical charge coulombs per cubic meter. Okay, so this is everywhere. This is defined everywhere in space. But now we have a certain path in space. You see, it's not very technical. It's just sort of playing around with t, and this spatial curve should be the one having coordinates t squared, t cubed. Please don't be confused about this exponent capital T. This always means transposed, because a vector in matrix and vector calculus, or matrix and vector algebra, is usually given to be a column vector. And if I save some space by putting it as a row vector, I always use this transposed symbol. Just don't care. Okay. Now, this is the path in space, and t increases from 0 to 1. Now, we have a certain problem. We want to calculate the total amount of electric charge along this path, which is, as you know, a one-dimensional object. And now, on the other hand, we have a spatial volume charge density in the unit Coulomb per cubic meter. So how do we bring this together? Well, the answer is, it makes sense to assume that, well, let's just assume there's a certain piece of plastic, you would say bent exactly along this path. And this contains some electric charge. So you could say it is electrostatically charged. And in practice, of course, a one-dimensional path does not exist as a physical object, because it would be, well, infinitely thin. But we must assume some thickness, otherwise we don't get anything. And the thickness I assume here is given in the form of a so-called cross-section area, which is practically, well, so I just chose it to be A equals 1 squared millimeter. So please note that if I use millimeters squared and then transforming to standard international units, I must remember that a millimeter is, of course, 1,000th of a meter, but in the squared version, of course, this means to be 10 or -6 squared meters, right? So this is like, you could say, micro square meters. The factor is 1,000,000 to transform from square millimeters to square meters. That's okay. And then we can start by saying, since this is a non-directional property, as you see, the row of x vector function equals 2x plus 9z. There is no y contained. Well, it's and that's the way it is. Okay, we just take it. But as you see, this contains no directional information. So we just take it as a scalar function, rho of x vector, and then times, actually this is sort of, first of all, it's a volume integral. We must sum this up, multiplying with infinitesimal little pieces of volume, and then summing up, we get the total charge. I mean, this makes sense, right? Because Coulomb per cubic meter times cubic meter gets Coulomb in the end, standard symbol for charge, electrical charge along the path. Now you may wonder, how can I perform a volume integral along the path? Well, the answer is I have a constant cross-section area to multiply to everything. So if I assume this to be inside the volume element, I just extract it from the integral, and then I get a regular path integral over the path rho of x vector. And now you see, this is scalar, of course, because the volume in that sense doesn't have any direction. But then using a directional differential vector here wouldn't make sense. I am allowed to use absolute values here. So that's always the case if the function that I'm integrating along a path is not directional. If it's a scalar function, I may use absolute values, right? You know this from type 1 path integrals. Look at here. Imagine the black curve would be our path, okay? And then in blue, I just illustrated to you how to imagine this cross-section area A valid along the whole path. Okay, that's sort of what we're doing. This would be a differential spatial movement vector, dx vector. But if I multiply it all the time with this cross-section area, here you see it, A, then I get my differential volume, formally. But then again, well, I should say absolute value of differential x vector. That's the way you write it, usually. That makes more sense. So roughly speaking, that's what we do. You don't need to understand it in detail, I guess, for now. Well, but that seems to work, okay? So let's just take this A as a prefactor and then integrate and now perform or transform this integral as usual to a form that contains t only as a variable. So we integrate from 0 to 1, that's clear, this is our interval for t. Then we evaluate the rho function of x vector of t, which means we calculate the valid volume electric charge density for a corresponding value of variable t by, as always, filling in the components, the 3 different components of the path radius vector function to the appearances of coordinate x, coordinate y, which doesn't appear, and coordinate z in the rho function. So that's what I'm doing. And also I need, as always, for the substitution here, I need to put an additional factor of sort of velocity at this place, physically speaking, which is the x vector dot of t, which allows me to replace the spatial differential vector for a temporal differential dt. Also, since this is scalar anyway, because it's one-dimensional, I don't need absolute value signs here. Here I do, here I don't. But that's just you could say that this taking the absolute value is delayed to this place where this still directional x vector dot of t is well, where its vector properties are removed by taking the absolute value. So let's just go on. The integral of a non-directional scalar function along a path p, this is what we are calculating. Note that we have to take the x vector dot of t, which means differentiating all the components for t. T differentiated gets 1, t squared gets 2t, t cubed gets 3 times t squared, that's all. And then we take the absolute value because the direction is not of any interest here. As always, using Euclidean metrics, right? It's sort of 3-dimensional Pythagoras theorem. Square root of 1 squared plus 2t squared, this quantity squared, right? And 3t squared, this quantity squared. So that's, in the end, it's 1 plus, look here, 4 times t squared, and also plus 9 times t squared squared, where squared squared gets power of 4. So that's 9t power 4. Okay, you might recognize that I constructed this exercise in a way so that we find an integral that may easily be solved. So this is sort of a little artificial. I don't want to play any tricks on you, right? So if I had chosen a more complicated function here, it might be that this integral is not even analytically solvable in the end. So I wanted to avoid this, and that's why I used a little trick and chose my rho function in a way that it turns out to be sort of the derivative of the radicand function here for our comfort. Okay, but just don't care. So inserting A, the cross-section area, to be 10 power negative 6 in SI units, in the unit m squared, which I leave away here. Then integrating, what is this? That's important. We have, as we said, we have to insert points, points in space lying on the path into the vector field. Much the same technique as in the exercise before. So use t for x, use t squared for y, and use t cubed for z. So that's why I put 2 times t here, because t has to be used for x, plus 9 times z, and the z coordinate is t cubed. So in the end, I get 2 times t plus 9 times t cubed. That's what I get, what I have here. And then times this square root expression. And now look, in order to solve it, we have, in some way, we have to use a certain substitution. So that's clear. Because this is a nested function, it would be a case for the chain rule when differentiating. So we would take, we must, in some way, we must use the inverse chain rule, which is called substitution. And that's what I'm doing. I just try and substitute the radicand for u. So u equals 1 plus 4t squared plus 9t power 4. If I do so, I have to take the differential form also. You remember from integral calculus how to do this. U gets du, term gets differentiated, one additive constant disappears. 4t squared differentiated gets 2 times 4 times t, so it's 8t, plus we get 9 times 4 times t cubed when differentiating, and 4 times 9 equals 36, so we get 36t cubed, and then times differential dt. So that's, you could say, this is the derivative of t as of u as a function of t, but then with separated differentials. Why do we do this? Well, to express everything inside the integral for by the replacement variable u. This refers also to the limits, 0, 1, they must be adapted, and also to the differential. Well, now it turns out I might put a factor of 8. Could I? No, not really. But it's quite obvious I can extract a factor of 4, common factor. So if I do so, this is 4 times, and then in parentheses, only 2t plus 9t cubed. And now we are lucky, because this is exactly the prefactor which is by chance given to be the charge density rho. So that's our big luck, you could say, because now we can do the following. Well, replacing everything. Dt, well, let's start here. The square root of this term, of course, is the square root of u. That's what we want, right? But also dt, if I isolate dt here, I could, well, how do I do it? Well, the best idea would be dividing this equation, let's do so, by 4, if you want, right? Divide by 4, and then you get, in the end, you get 1/4 times du, and that's what I use. Look here, 1/4 times du. And this is what I use instead of, look here again, instead of this 2t plus 9t cubed times dt. Look, this factor times dt is replaced by 1/4 after dividing by 4, 1/4 du. So that's a little tricky here, but in the end, that's everything we keep inside the integral. And we got rid of this whole nesting, and it's easy to solve now. But please don't forget to also replace the limits, which are, as you know, t values, and now expressing them by u. How do you do this? It's simple. You just insert these t values into your substitution. So if t equals 0, I just insert here, then u equals 1 plus 4 0 squared plus 9 0 power 4. So 0 0 1 remains. 1 for u. 1 for me, 1 for you. No, 1 for a variable u. Now the upper limit 1 also is a t value. Inserting here, I get u equals 1 plus 4 times 1 squared plus 9 times 1 power 4. And what is it? It's 1 plus 4 plus 9, which is obviously 14. It's equal to 14. That's the upper limit for u. Now, taking the primitive function, you remember this comes from here. Well, this is u power 1/2 in the power notation. We increase the power by 1. So we get u power 3/2. We divide by the new power, which is dividing by 3/2, or in other words, multiplying by 2 over 3. And then putting this together with the 1/4 prefactor, look here, it's 2 over 12. Shortened, we get 1 over 6. That's it, times micro, so times 1 millionth, and then times, now inserting our values, 14 for u. Now look, this goes, well, it's not really that easy. If you don't use a calculator, you just put it in the most pretty analytical form. So we get u power 3/2, which means, let me see, it means 14 power 3/2. And I say this is 14 power, let me think, is that even true? Ah, yes, right. Look, we could say it is 14 power 3/2, and this can be split to be 14 power 1/2 and then power 3. That's a possibility. Fifth law of, fifth potency law. Let me just explain it a little bit. So, and yeah, and then I can say in the parentheses, this is square root of 14 and then power 3. So in other words, square root of 14 times itself. And this can also, again, these two can be put to be 14, a factor of 14 times square root of 14. So I'm sorry, there are different ways to reach this form. You don't need to use it, but it's the most compact, I think, or pretty a way of writing it down. I would say, what else could you do? Never mind. Okay, so it's 14 times square root of 14. Then minus 1 for u, then I get 1 power 3/2, which is still 1. So evaluating this, since it's a physical example, we should take the calculator, and it turns out in Coulomb, in the unit of electrical charge, which is Coulomb, we get around 8 for 2 significant digits here. This is the precision you usually take. You could also use 3 significant digits perhaps, but I think this is precise enough. So we get roughly 8.6 times 10 power negative 6 coulombs, which is usually abbreviated to be 8.6 micro coulomb. This is, of course, a very small amount of electrical charge, if you want, but on the other hand, look at the given functions and numbers. This is what we have. It's also due to the fact that this cross-section area is quite small. So anyway, that's the solution of this optional additional exercise. And this is also the end of sheet 10.1, or is it even 10.2? Sorry, I even forgot. No, it's 10.1, right? Yeah, and we will shortly dive into the first exercise of the next sheet even, which is about surface and volume integrals. So, thank you.